We will work on a few examples on mechanical energy conservation in this lecture. When using conservation of energy, we can follow these steps. First, define the system. Choose a zero level for height. Identify the initial and final points. Write out the conservation of energy equation, and then solve for the unknown variable. Let's first start with a conceptual example. In this swimming hole example, a person swims on a rope. Can we use the principle of conservation of mechanical energy to find his speed at the bottom? So, reading the question states there are three forces acting on him: weight, tension, and the rope. Now, always remember, conservation of mechanical energy requires that the work done by non-conservative force is zero. So we have to distinguish those three forces. Which force is conservative? Which force is non-conservative? Apparently, gravity is conservative. How about tension and the rope? Tension is not conservative. Air resistance is not conservative. Okay, so we have to analyze whether they do work to the person. Acting on the person doesn't mean it has to do work, right? So, and the requirement for mechanical energy conservation is that non-conservative force does not do work. Now for the tension force is always perpendicular to the person. Perpendicular to the velocity of the person at any instance. Tension, velocity. So tension doesn't do work. So we're left with air resistance. If air resistance cannot be neglected, then it does do work to the system. And air resistance does negative work. Now, because non-conservative force, which is air resistance, is doing work, mechanical energy is not conserved. So the answer is no. We cannot. So, but we can use conservation of energy to solve this problem only if air resistance is neglected. Then we can use conservation of energy. Okay, let's move on to a more quantitative example. So we have athlete lifts the trampoline at an initial height of 1.2 meter, reach a maximum height of 4.8 meter before falling back down. What's the initial speed? So in this example, apparently we can neglect air resistance. Then mechanical energy is conserved. So we have initial energy equals final energy, and the initial energy equals kinetic energy, potential energy. This initial kinetic energy, initial potential energy equals final kinetic energy, final potential energy. Okay. The equation for initial kinetic energy given by 1/2 mv squared mgh0 initial height, final kinetic energy, final potential energy. But what's the final kinetic energy of the person on the highest point? So on the highest point, the velocity has to be zero, right? So this term is zero. We're left with 1/2 mv0 squared equals mghf. Subtract mgh0 from both sides, and m would cancel. So v0 squared would equals to 2. So v0 is square root 2 g hf subtract h0. Put in the numbers, we find the initial speed is 8.4 meter per second. Okay, let's look at another example. We have a motorcyclist trying to leap across the canyon by driving horizontally off a cliff with initial velocity pointing in the horizontal direction 38 meters per second. Ignoring air resistance, find the speed with which the cycle strikes the ground on the other side. It only asks us for speed, it doesn't ask for velocity. And the big difference is that for velocity, you need to find the x component and the y component. For speed, you just need to find the number. And we definitely can solve speed from final kinetic energy. So for this one, when the cyclist is in the air, only gravity is doing work on the motorcyclist, so mechanical energy is conserved. So we can convince ourselves mechanical energy is conserved, and the final mechanical energy, this is final potential energy plus final kinetic energy equals to initial potential energy, initial kinetic energy. So cancel all the m's. I think maybe it's easier. We can also multiply a 2 to each of the terms. Multiplying 2. Okay. And we want to solve for final speed, just speed. So we get the equation that we can solve for our final speed. If you look at it again, it's the square root of the right hand side. Now all we need to do is just plug in all the numbers from the problem, and we find the final speed is 46.2 meter per second.